In digital electronics, every complex circuit, no matter how intricate, can be physically reduced to a single repeating building block, the NAND gate. Continuous mathematics has never had a single primitive. To calculate exponents, logarithms, and trigonometry, we rely on a massive, highly redundant catalog of distinct operations and rules. Before computation was automated, early quantitative scientists managed this redundancy by pre-calculating physical books of logarithms and sines, column by column, to look up values by hand. Later, mechanical devices like the slide rule mapped these different mathematical operations onto physical space, using misaligned scales to compute complex multiplication and exponents. Today, this historical fragmentation is permanently etched onto the scientific calculator. We have dedicated keys for sine, cosine, tangent, natural log, and square roots. We digitized the math, but we never unified the foundation. Computations that model the physical world still require researchers to juggle dozens of disconnected algorithms. Physicist Andrei Audrey-Wallach proposed that this diversity is not a strict requirement of continuous mathematics. His research proves that the entire standard vocabulary of a scientific calculator can be derived from a single binary operation. He calls it the EML operator. It takes two inputs, x and y, and applies a precise formula, e to the power of x minus the natural logarithm of y. To function across all of mathematics, it is paired with only one terminal constant, the number 1. The constant 1 serves a mechanical purpose. When you substitute 1 for the y variable, the natural log of 1 evaluates to exactly 0. This neutralizes the logarithmic half of the operator, leaving only the exponential term. By repeating this single operation, disparate mathematical functions can be compiled into uniform binary trees. This allows diverse mathematical operations to be processed as identical, predictable components within machine learning architectures. The EML operator takes the sprawling, highly varied syntax of calculus and standardizes it into a single computable grammar. Isolating this new operator required systematic ablation. The methodology was straightforward. Take the standard list of mathematical operations, remove one ion, and verify if the remaining set could still reconstruct it. This table tracks the reduction. The search began with a parameter space of 36 standard primitives, named constants, unary functions, and binary operators. Iterative testing stripped away the redundant elements. The list was reduced to 6 items, and then to 4. Retaining subtraction, a non-commutative operator, was essential here, because its mathematical asymmetry allows an expression tree to grow and invert its outputs. Further reduction absorbed the constant e directly into the exponential function itself, leaving a system of just 3 primitives. The final deduction required recognizing a pattern across these minimal configurations. Pairing inverse functions, the exponential and the logarithm, at the input, and feeding them into an asymmetric subtraction at the output, collapses the entire system into the single EML operator paired with the constant 1. The exhaustive search demonstrates that the perceived complexity of continuous mathematics is largely an artifact of human notation. To verify the operator's universality, it has to constructively derive the foundational constants and operations. This was done through numeric bootstrapping, substituting independent transcendental constants into the equations to prove formula equivalence. The simplest constructive proof generates Euler's number, E. If you feed the constant 1 into both inputs of the EML operator, the equation becomes e to the power of 1 minus the natural log of 1. Because the log of 1 is 0, the operator outputs exactly e. Extracting the natural logarithm requires deeper nesting. The tree structure for the natural log of z requires applying the EML operator 3 times, routing the constant 1 and the variable z through a cascading sequence. Inside this specific tree, the inputs force an internal algebraic cancellation. The arrangement generates a 1 over z term inside a complex exponential, which isolates the logarithm and neutralizes the remaining variables. From there, the tree deepens. Addition, multiplication, square roots, and hyperbolic tangents. Every standard function is simply a progressively larger branching arrangement of this same node. Through repeated self-application, this singular formula constructs every function required by quantitative science. Generating constants like I and pi, along with the trigonometric functions, requires the EML operator to calculate outside the real number line. This graph illustrates Euler's formula, which provides the strict geometric bridge between exponentials, logarithms, and circular trigonometry. When the EML operator is forced to evaluate a negative input across the negative real axis, taking the natural logarithm of -1 via the principal branch forces the output to rotate into the complex plane, yielding I times pi. The topological consequence of this framework is complete replacement. A complex trigonometric equation can be mapped perfectly into an isomorphic, uniform binary tree. Every node in this space is governed by a trivial, context-free grammar. The output is always either the constant 1 or the EML operator applied to two previous nodes. The EML operator regularizes mathematical syntax into a uniform tree structure, accessible to standard gradient-based optimization. This uniform grammar provides a new way to solve symbolic regression, the task of discovering a closed-form mathematical expression from numerical data. Because the grammar is identical everywhere, researchers can construct a parameterized master formula. This is a binary tree of arbitrary depth, where every node is an EML operator. Each node utilizes a routing architecture with three inputs: the constant 1, the variable x, or f from a previous node. Alpha, beta, and gamma coefficients act as gates. Setting alpha to 1 routes only the constant 1, blocking the others. By tuning these coefficients, this master architecture guarantees that the model search space contains all possible mathematical operations up to the maximum depth of the tree, eliminating blind spots. During optimization, the routing parameters alpha, beta, and gamma are initially treated as continuous logits. They are passed through a softmax function to normalize them into fractional probabilities. As the atom optimizer trains the network, it adjusts the continuous weights to fit the numerical dataset, causing the regression curve to fluctuate. Standard neural networks stop here as opaque black boxes, relying on fluid, continuous decimal values. The EML tree undergoes a hardening phase. The optimization forces the fluid, continuous decimal values to collapse into a rigid, discrete geometry. The continuous weights snap perfectly to the exact vertices of a simplex. Every coefficient becomes exactly 0 or exactly 1. The fluid approximation collapses into a strict binary tree, directly translating into an exact symbolic equation. The continuous Sheffer stroke upgrades neural networks from approximate pattern matchers into engines capable of discovering the exact interpretable laws of nature.